Okay, so last time, um, ooh, this transcription's on. I think I want to turn that off. Okay. All right. So last time we talked about uniform motion. That's just motion with constant velocity. So last time was just essentially uh, your velocity over time uh, is essentially some sort of constant. And if we were to plot it, velocity, time, you just have a straight line. Now what that means for your position, in turn, that means your position over time would actually be it'd be aligned with a linear slope, so the same slope everywhere. Now, for this next part, we're actually going to talk about acceleration. So essentially what happens when your velocity is also changing, and then what does that do to your position as a function of time? All right. Um, so, ooh, a little laggy. All right, there we go. So let's consider the following race here. Suppose the driver of a Volkswagen Beetle wants to race the driver of a Porsche. Okay, and the goal of this would be for both drivers to at least achieve a 30 meters per second speed. Well, obviously both are capable of reaching that speed. So how can we actually compare the performance? Um, if we're trying to achieve a goal that both of these cars can achieve, what's going to be the deciding factor on essentially who is faster, who does it better? Um, so although we know how this is going to turn out, let's go ahead and take a look at this example. Uh, so to do that, what we can do is look at each car's acceleration. So that's going to be essentially, even though they're both getting to a totally doable speed for both vehicles, the question is how fast can they get to that speed? So let's look at the velocities in tenth of a second increments. Okay, so here we have the velocity of, there we go. So we have the velocity of a Porsche and the Volkswagen Beetle here. So you'll notice that the Porsche, as we go in a tenth of a second increments, as this increase is going down, you'll notice that by the time we get to 0.4 seconds, the velocity in meters per second of the Porsche is already 2 meters per second, whereas the velocity of the Beetle is much slower. It's just not even up to a meter per second yet. So clearly they're both on their way to 30 meters per second, but the issue is the Porsche is getting there much quicker than the Volkswagen Beetle. So here the idea is over the same time interval. Okay, so we're looking at just these first few seconds, right? Okay, so over the same time interval, the velocity of the Porsche increases more than the Volkswagen. Okay, so this is the same time interval, and the idea is that there's an increase in velocity that's greater than a different increase in velocity. And of course, we can represent that by a steeper slope on the velocity versus time graph. So you can see down here, we have the velocity of the Porsche and the velocity of the Volkswagen. And the idea here is, like in the case of the Porsche, as we move over in time, okay, for each time step that we're taking, we're adding more velocity. So this is going to be a bigger plus v than what the Volkswagen is adding. So these vertical chunks that we're adding as we move to the right, they're going to be smaller for the Volkswagen than for the Porsche. So you'll notice that because we're adding bigger chunks for the Porsche is going to get to 30 meters per second much faster than the Volkswagen is. Okay. With that being said, what you'll notice is essentially the slope on these two velocities. Just like we talked about last lecture, the slope here, they're also straight. These are linear as well. Okay, so what does that mean about the derivative? If our slope is linear, if slope's a straight line, we know that the derivative is going to be constant. Okay, so the linear velocity means that we're going to have a constant acceleration. Okay, and that just means, just like we had the uniform motion with the velocity, we can call this uniformly accelerated motion. Okay, uniformly accelerated motion. And we get this if and only if, that's another math term, if and only if. So I may abbreviate that in the future as just IFF. That's how mathematicians abbreviate that. Just an aside in case I'm writing in a hurry and that happens. Uniform accelerated motion happens if and only if the acceleration is constant. So if the acceleration is constant, that means our velocity versus time is linear right here in the graph. We can see that. Okay, and then we need to talk about what that means for our position versus time. Okay, so we're going from constant linear to something else. We'll get there shortly. All right, and in this case, the straight line slope, well, that's just your average velocity, just like last time we talked about, that's your average acceleration, just like last time we talked about average velocity. Okay, well, we can start applying this whole idea like we did last lecture, where we talked about the change in position over change in time. Well, that gives us a slope and that gives us a velocity. Well, here, the change in velocity over change in time, that's going to give us our acceleration. Okay, so we see from the graph that the Porsche achieved a velocity of 30 meters per second in only 5 seconds, while the Volkswagen actually took 15 seconds. All right, now we can do some calculations with this. So what do these values actually tell us about the rate of change of their velocities? All right, well, we can essentially just plug and chug in this slope equation that we have. We know that the initial time and initial velocity, those are 0. So those go away, and we're essentially just left with this final velocity divided by how many seconds it took to get there. So we know it only took, this up here should be 6 seconds. There, I'll fix that. Okay, so the Porsche did this in 6 seconds, not 5. All right. So we know that the Porsche did this in 6 seconds. Okay, so that's just going to be the final velocity divided by the time it took to reach that velocity. Well, that's going to give us an acceleration of 5 meters per second squared. You'll notice we have that unit of meters per second, and that's the units of acceleration. Meters per second squared is how we say that. Same thing down here with the Volkswagen. We've got the 30 meters per second that it needed to reach, but it did it in a much longer time, 15 seconds. So that means the acceleration of the Volkswagen is only 2 meters per second squared. So this is each car's change in velocity per second, right? So again, these units are meters per second or meters per second squared. So this is important. You'll hear me say meters per second squared quite a bit. So essentially what this means is that the Porsche adds 5 meters per second to its velocity every second that it's in motion. So it'll be the first second it was moving with a velocity of 5 meters per second. After 2 seconds, it's already up to 10 meters per second, then 15 meters per second, and it just keeps building. Same thing with the Volkswagen. It's going to add every second, it's going to add 2 meters per second to its velocity. So we're adding to the rate, we're not adding to the position like last lecture. Now we can actually start using some of this to build some more kinematic equations. So we already have a kinematic equation, actually a couple, I guess, of kinematic equations from the last lecture. So let's see if we can build up something new here. All right, so using the same idea from the constant average velocity, we're going to essentially use the same mathematical template to build some equations with constant average acceleration. All right, so we know that the average acceleration just is equal to the change in, we'll call it rise over run, the change in your y versus the change in your x. Okay, well, we can do the same thing from the last lecture. And essentially, we can just say, well, average velocity just equals the difference in final and initial velocity divided by the amount of time it took to do that, the delta t. Okay, well, that's our rate. And if we sort of ignore these intermediate steps that we all know is just the slope equation, all we can do is just set the left-hand side and the right-hand side equal to each other and solve for the final velocity. We can simplify this since, you know, the average acceleration, we know that's constant now because we're dealing with constant acceleration. So we can simply just write it as a. So here's another useful kinematic equation that deals with motion with a constant acceleration. And you'll notice, just like in the last situation where we had our position, our final position equals the initial plus velocity times time. Here we have a very similar situation, but we've essentially taken that derivative. We're looking at the rate instead of just the position. Everything works the same way. So you'll notice that it's just a linear slope equation again. So we have the y equals mx plus b look once again, except this time we're dealing with changes in rates instead of changes in position. All right, so again, we can also talk about this idea of instantaneous acceleration. So with an instantaneous acceleration, just like with an instantaneous velocity, well, we can approximate that. You'll notice here I've updated this chart from the last lecture. We have velocity as a function of time, and we're looking at this green line. And if we suppose we want, you know, the slope of the velocity versus time graph at point t2, at time t2, well, that's essentially going to be a very particular acceleration because the acceleration is changing on the green line there. So again, all we need to do is just let that delta t, we can take t1, t2, or t1, t3 if we're calculating the average acceleration with those, apply the limit, make that interval really small, and then again, we just have a derivative. So it turns out that the acceleration is just the derivative of the velocity versus time plot. We can also go the other way. So perhaps we have information about the acceleration. So the final step here, the final rate that we're looking at. So if we have that information, we can actually go backwards to get information about velocity. It works the same way as the last lecture. So if we have just the initial velocity, but we want to add those steps to it, this again is going to be the same process. We're going to add up those small intervals along the velocity versus time graph. No, we're going to add that up along the acceleration versus time graph, and that's going to let us step backwards to get velocity information. So you can see over here on the right, if we have, instead of f of x, this would be our acceleration versus time. This down here would just be a delta t. And what's going to happen is when we add up all these, when we integrate, that's going to give us information about velocity as a function of time. So essentially, it's just this whole process is the initial velocity plus the area under the graph, which is just an integral. Now let's think about what this means as far as the calculus of these kinematic equations. If we start with our position as a function of time, so where we are and when we're there, if we take that plot and we take the derivative of it, well, that tells us how fast we're moving at these points as we get to the point and as we leave the point. That's going to be our velocity, which is the derivative of position. Okay, so position. Here's our velocity. We take another derivative. Well, that's going to be our acceleration, so our change in velocity. So we have position, rate, rate, there we go. And then change of that rate. All right, now, if we do that, you take two derivatives, we get to acceleration. If we go backwards, if we integrate, that's how we can step backwards from the change of the rate to the rate, and then from the rate to the actual position. So as you remember from calculus, differentiating goes one way, integration goes the other. Now, let's think about what we can do with this information here. So assuming constant acceleration, all these kinematic equations that we're building here are going to be with constant acceleration assumed. All right, well, if the acceleration is constant, that means the graph of the acceleration is always going to be a straight line. That means this value here, the a sub s, well, because the acceleration is constant, no matter where we are on this plot, it's always just going to be that value, no matter where you go, no matter what time your acceleration is always going to be the same. Okay, so what does that mean for our graph of velocity? Well, that just means that the slope is going to be a straight line forever and ever. So if you look down here to our velocity versus time, okay, so these plots are going to inform each other. So our velocity versus time, no matter how far we go, it's going to be the same slope no matter what. Now, that being said, we have this nice velocity versus time graph. It's all labeled. So that means what we can do is actually just find the area under this curve. I know it's a straight line, but we can still integrate it. We can integrate straight lines. So the idea here is, let's take this velocity versus time graph where there is an acceleration, where there is a slope, and actually integrate it. Well, the integral is just the area under the curve. Okay, so that's going to be the initial position plus this bottom rectangle. Okay, so I'm going to highlight it here. Plus this bottom rectangle, plus the top triangle, okay? We can actually exactly calculate this area under our very easy curve here. Well, the bottom rectangle is just length times width, okay? So that's going to be, looks like we have a delta t for length or width, and then we have this initial velocity, right? So this initial value, how fast are we going when we start the stopwatch? What is our initial velocity? Well, multiplying those two things together, that's going to be the area of our rectangle in the bottom. Well, then the top triangle is just 1/2 the base, which is delta t, right? It's the same length here. It's still delta t, and then times the height. Well, the height is actually acceleration times time, right here. All right, well, let's write that out. Okay, so we have the rectangle plus the area of the triangle, and it looks like we have a delta t times another delta t there. So what we can do is essentially just write that as delta t squared, and then here is another kinematic equation that you can use. It does assume a constant acceleration. However, it includes everything we've talked about. We've got that position component, we've got a velocity component, and we have the acceleration component. So this is a very powerful tool because it includes all of these pieces of motion all in one equation. So essentially, at some time, if you know all this stuff about a moving object, you can tell where that object is going to be at a later time. All right, so that means we actually have a couple different kinematic equations here. So we've already derived this first kinematic equation where we can actually calculate the final velocity. We just looked at number 2 here, the position versus time with an acceleration. Now, to obtain this third equation, I'm leaving it as a problem on a problem set. But what you want to do to actually build and just construct from first principles this third equation, what you want to do is you want to solve equation 1. You want to solve for delta t. So delta t equals stuff. So delta t equals, you want to fill in what's there. And once you do that, you'll plug it in here. Okay, so you'll have delta t equals a few terms, plug that in, and when you turn the crank on the algebra, you're going to get equation number 3. I do suggest you look at the text I've posted. This is done, it doesn't include all the steps, but it includes a few steps so you can check your work along the way. So essentially the idea here is that you can actually take these basic equations and build some new equations of your own that maybe you're looking at a situation where the basic equations won't really help you. You could build something that can. So the cool thing about number three here does not depend on time. Does not depend on time, which is very helpful because sometimes you don't know maybe how long something's been moving, but you can actually ignore that time parameter and still do calculations without knowing just how long something took. So another thing to point out here, we have two situations over here in these plots. We have a motion at constant velocity. Okay, well, if velocity is constant, that means our acceleration is 0. So no matter where we go on this plot, we just have 0 acceleration. Okay, well, if we have 0 acceleration, that means the horizontal line, that means the velocity will be a horizontal line. So now we have this constant velocity. No matter where we go on the plot, our velocity is going to be the same value. So that means no matter what period in time we're looking at, object has same velocity. Now, since that's the case, that means our position as a function of time is going to be linear. It's going to be a straight line. Now let's consider the situation where we do have an acceleration, and it's constant. So that means our acceleration is still a horizontal line, but it's no longer 0. It actually has some value. Okay, so it's been moved up here. It has some value. The question is, what does that do to our other plots as we integrate? Well, a straight line here means if we integrate, we get a slope. All right, so that's our velocity. Our velocity is always changing. In this case, we're adding for each step in time. We're doing like a plus v. We're adding to it. Now, since this is the case, since we have a constant acceleration, that means for our position, it's going to be parabolic. So that's going to be a nonlinear shape. Okay, so now we have this nice nonlinear position as a function of time. And, you know, that kind of makes sense because the thing that we're adding with each step, so we're adding a position here with all these little steps. But the amount that we add each time, because we have an acceleration, the plus distance we add keeps getting bigger because we're accelerating. And it's not just the same chunk of distance we're adding each time. There we go. All right, now let's look at a quick example here. So we've got this issue. We've got the Leaning Tower of Pisa. It leans at an angle of 4 degrees. Okay, that means essentially, if we look at it this way, we've got a slight angle here of 4 degrees. I hope that looks all right for you guys. So that also means instead of having a nice 90-degree angle down here in the corner, we actually have an angle of about 86 degrees down here. So we're not dropping something from like just a nice perfect perpendicular angle. We've got a little bit of a lean. All right, so we're dropping the Leaning Tower of Pisa, or sorry, we're dropping something off of the Leaning Tower of Pisa. Looks like we have a ball, and we're dropping it from the tower. The question is, given the fact that the Leaning Tower of Pisa is 55.86 meters tall, what speed would this ball hit the ground when we drop it? All right, well, notice that we don't have any information about a time. We don't have a stopwatch. At least the problem doesn't say we have a stopwatch. So that means we need to use this new equation that you're going to build in a problem set to actually calculate the final velocity of this ball when it hits the ground. All right, so we've already done the two first steps. We've modeled and we visualized. Now we just need to figure out our knowns and unknowns and actually do the math. This is where the physics happens. All right, so we know our initial velocity. This is what we know. It's going to start at rest since we're holding it still and we let it go. Now, this number here, this negative 9.8 meters per second. So this value is actually it's called free fall or acceleration due to gravity. And this is essentially always the same, no matter where you, almost always the same. There's a little bit of differentiation as you move around the planet, but this is always the same when you drop an object and it's not really influenced by air resistance. This is always going to be negative 9.8 meters per second squared. So essentially negative 9.8 meters per second squared is free fall acceleration. And a lot of times this is actually represented by g for gravity. So here our acceleration equals g. I put the negative there because g usually is just the magnitude, the 9.8, but since it's falling, it's going to be negative g since we're moving in the negative y direction. So if we were going to draw this out, this would be our x. We don't have any motion in the x direction, but we do have motion in the y direction. So you can think of a Cartesian grid. All right, so now we know where this negative 9.8 comes from for our acceleration. Now we just need to figure out our delta y. So how far does this thing move through the atmosphere here when it hits the ground? Well, we need to do a little bit of trig. Okay, so we know the height of this thing is 55.86 meters. Okay, well, we need to find the opposite side of this angle. So we're going to use some trig. We're going to do the old SOHCAHTOA, right? And we need the opposite side because we have the hypotenuse. The hypotenuse is just the length of the whole tower. Okay, so it's going to be a sine of that inside angle here, which I've labeled as 86. All right, so now because of that lean, we know that we're going to drop this thing from 55.72 meters. That's our delta y. All right, our final distance, well, it's going to hit the ground, right? So it's not going to have any y value. It's not going to have any height when it finishes. So it's going to hit the ground, be 0 meters, and then we still have that initial height of 55.72. That's going to give us a negative delta y. Now we can just plug in all this information that we have. We know the initial speed, 0, a velocity of 0 meters per second. That's easy to deal with because 0 squared is 0. Okay, so that's going to be plus 2 our acceleration, which is our free fall acceleration due to gravity. Okay, and that's going to be multiplied by that distance, which keep in mind is negative because we're falling in the negative y direction. I'm going to notate that right here, negative y direction. Going down. All right, here you have negative y. Now, we just have to essentially turn the crank, and when we do, turns out the final velocity when this thing hits the ground is going to be 33 meters per second. All right, let's look at one more example. So that was with an object in free fall, which is always going to be under the influence of gravity, which is 9.8. And for most common uses, gravity will always be negative 9.8 meters per second down. That will be a little less, like if you go up to Boone, up in Western North Carolina, gravity is like negative 9.79. So it's really close. For most applications, you can just use negative 9.8, and it stays pretty constant. So let's look at one horizontal example where we have two things moving at once instead of just one ball falling or something. So in this case, we have two cars, and they're driving side by side in adjacent lanes on the freeway. Okay, well, I've modeled that. I've visualized here. Started to write down the things I know and I don't know. So first of all, I got my two cars, all right? They're both cruising at 75 miles per hour. Well, I need to convert that. That's going to be 33.5 meters per second. Okay, so I've notated that in my visual over here. So a pickup truck ahead of one car loses an object off the back. Okay, the car following the truck, which is car A, skids to a halt. Okay, so we know there's some object here. It's going to be in the way of the car. All right, and then this car A is going to skid to a halt. So that means it's decelerating. That means, again, we have a negative velocity. So we started with a speed. We have to start subtracting. Okay, we either need to subtract until that speed hits 0 or subtract until that speed hits negative. So just like in the last problem, we're subtracting because we wanted a negative velocity. It's falling in the negative y direction. Same thing here, except we just want to subtract till we hit a velocity of 0. All right, so the car is decelerating. That means it's going to have a negative velocity. The other car, on the other hand, car B, that continues driving at a constant speed. Okay, so essentially, car B is not affected at all. So the question is, how far away, and we can specify, we can say how far away from the origin is car B. Okay, so as car B keeps going, how far away do we get when this car A up here stops at this object? All right, well, we've modeled and visualized, so we're good to go. So let's jump into actually using some equations. So we need to get more information from car A. Well, we need to figure out how long it took for this car to stop. Okay, so if we can figure out how long it took to go from its cruising speed to 0, we can use that information to figure out how far car B went. So the idea here is to use time as a link between the two objects. So that's worth noting. So use time as a link between the objects. All right. So let's start with this equation here. We know final velocity, we know initial velocity, we know the deceleration. Now we just need to solve for time. So this kinematic equation is going to be very useful for us. We can solve for this delta t. Keep in mind, this is the expression you'll need to use when you're deriving that other kinematic equation. So you may want to jot this down and use that later on in your problem set. But this calculation is pretty easy. We know our final velocity is 0. We know that the initial velocity is 33.5. And then we know that our deceleration, remember this is deceleration, this is going to be negative. Okay, so our negative 8 meters per second squared. And that's going to give us a deceleration time of about a little over 4 seconds to go from 75 miles per hour to a full stop. Okay, well, we want to know how far car B goes in that 4 seconds. So the same thing, we need to apply another kinematic equation. However, we're talking about distance in time now, not a changing velocity in time. So what we can do is essentially use our other kinematic equation. You'll notice that these two are very similar. One just deals with an absolute position, the one on the right. The other one deals with a rate, but they are related. So what we can do here is essentially just plug in what we know. We know our initial position, since we get to decide where the origin is, and that's going to be right where they're both side by side, and it's going to be right where and right when that object falls off the truck. As soon as that driver in car A hits their brakes, that'll be our t equals 0, and that'll be our origin. Now we can put in all this information. We know that it's going to be dealing with the initial position at the origin. We know that the car's cruising along at 75 miles per hour, which is 33.5 meters per second. And then we just use that time that we got from the previous part of this problem. Well, we know it's going to be traveling for 4.1875 seconds. Okay, when we plug that in, we're going to get a final distance of 140 meters. All right. And now we just have to assess. That's our last step. And 140 meters, that does seem reasonable. That's about a football field and a half in 4 seconds on the interstate. That sounds right. So, we don't have like, oh, it's going to go 10 million miles in 4 seconds. We would know that that's not correct. We also know it's not going to go like 3 centimeters in 4 seconds. So this last step is always useful. So once you get an answer, do take a moment, think about it, and make sure it's actually going to make sense. So as far as this problem goes, 140 meters seems to be about right. All right, so let's summarize real quick. So we now have these 4 wonderful kinematic equations that you'll be using throughout this course. They all have to deal with either your position and how that's related to your to time, or it has to do with your velocity and how your velocity relates to time. Although this last equation is kind of special, it gives us a nice statement that's not dependent on time, but it still gives us information about position and velocity. And then the only other thing you'll need to remember is essentially the calculus side of this. So what happens when you differentiate? What happens when you integrate? This all is a bit circular, but essentially you have a position, you have a rate. It's going to be your velocity, so how your position changes over time. And then you're going to have the change of rate. All right, so the problem set that goes with this is going to explore a lot of these ideas. There's going to be a few problems where you just have to do some basic calculations of where and when things are when they're under an acceleration. And then there'll also be some chance to actually do some calculus, take some derivatives, and figure things out that way. The only other thing I want to mention here is that G is acceleration due to gravity, and its magnitude, or its value, is 9.8 meters per second squared. Usually that'll be negative because things are going to fall in the negative y direction. It's going to lose height. But later on, we're going to play with coordinate systems and set them up in really weird ways. So there may be times when gravity is positive. That's totally fine. You just have to be aware of when to use the negative, when to use the positive. In our situation, usually gravity will be negative because we usually define up to be positive. And when things fall, they fall in the negative direction, requiring that negative 9.8 meters per second.